So now I will explain on the mechanics of lifting weight in the gym. In this video I will calculate the normal and shearing stress due to axial and torsional loading. So first, usually before you start your workout, you usually rotate the dumbbell to activate your muscle, or it means as you warming up your muscle. This will cause a torsional load to your arm and cause shearing stress. And as you can see here, it will create a torque, and this is a point C, where we will calculate the shearing stress using the elastic torsion formula. So now we will find the maximum shearing stress at point C, which is a point at the humerus bone. And we assume that the torque is 6 Nm, the outer diameter is 25 mm, the inner diameter is 15 mm. And we use, as I said earlier, the elastic torsion formula, which is the tau max equal to Tc over J. And we use this formula of polar moment of inertia. It is equal to 1 over 2 pi c power of 4 minus 2 c power of 4. So C2 here is the outer radius and C1 is inner radius, and C in this formula is actually the maximum radius, and we just substitute all the value and we can calculate the maximum shearing stress at point C, which is 195.57 Pascal. So next, when we lift the barbell, it will exert an axial load to the arm, and we can calculate the force created by the bicep muscle to withstand this load. So this is the diagram when we lift the barbell. WA, which is the weight of the forearm, WB is the weight of the barbell, FB is the force exerted by the bicep, and FE is the force exerted by the elbow joint. And this is the free body diagram to calculate the force of the bicep. So we in this free body diagram, R1 is the distance of the bicep from the elbow, R2 is the distance from the WA to the elbow, and R3 is the distance from the WB to the elbow. And we assume that R1 is 4 cm, R2 is 16 cm, and R3 is 35 cm. And also the WA is 25 Newton and WB is 50 Newton. And we put the point at the elbow where we assume that it is in equilibrium, so we can calculate the torque at E is equal to 0. And also in this calculation we assume that the elbow is in 90 degrees, so we can neglect the angle in this calculation. So we just substitute all the values and we obtain the force of the bicep exerted by the bicep to withstand the barbell is 537.5 Newton. So next, from the force from the muscle that we calculate, we can calculate the normal stress at point C, which is in the humerus bone. So we let the outer diameter is 25 mm and the inner diameter is 15 mm, same as I mentioned previously. And this is the formula for the normal stress, which is the force over the cross-sectional area. And firstly, we calculate the cross-sectional area at point C, and we obtain this value, and we just substitute, which is the F as we obtained from previously, the force of the biceps and the cross-sectional area, and we obtain the normal stress is 1.711 megapascal. And now I have covered the two learning objectives of solving problem of a body, which is the humerus bone and the muscle under axial and torsional load, and also I have covered the normal stress and shearing stress.
Okay.
Hello and good evening everyone. So today I'm going to talk about mechanics of material for stress and deformation. So deformation is a vector that represents a movement of a point in a body due to applied loads relative to another body point, and the shape and the size of the body is changed. This means being deformed, and value may be unchanged for some special cases. And the formula for stress equal to F over area, and deformation is equal to pressure multiplied with length over area multiplied with Young modulus. So firstly, I will show you guys our group video. So what happened in that video is our subject is workout, and suddenly he undergo a bone fracture at his hand. So from that video, I made a diagram to make you guys understand easily. So this is our diagram. So this is our subject's hand. He's wearing his hand orthosis. So there are total 4 forces exerted on his hand. So first one is force exerted by his bicep is going up, and force exerted by the elbow is going down, and weight of the forearm is going down, and weight of the belt is going down. So I assume weight of the belt is equal to 147 Newton, weight of the forearm is 25 Newton, and R1 is from force exerted by the elbow to the force exerted by the bicep is 0.04 meter, and R2 is from force exerted by the elbow to the weight of the forearm is 0.16 meter. R3 is force exerted by the elbow to the weight of the belt. R3 is 0.35 meter. So first of all, we will calculate the torque at the elbow. So the torque is equal to 0. So we want to find the force exerted by the bicep of the subject. So FB multiplied with 0.04 meter, and then minus, we put minus because the weight of the forearm is going down. So 25 multiplied with 0.16 meter, and then minus, we put minus again because the weight of the belt we assume force going up is positive and force going down is negative. So weight of the belt is going down, we put negative. So 147 multiplied with 0.35 meter, and then we can calculate and get force exerted by the bicep is 1486.25 meter, and then after that we can calculate the deformation of these cases. So the deformation, I assume the length of forearm is 0.35 meter, area of the forearm is 581 millimeter square, and our young modulus is 20.7 kilopascal. So the deformation, we use the deformation formula. So 1486.24 Newton multiplied with 0.35 meter over 581 multiplied 10 power of negative 3, and then multiply with 20.7 multiplied 10 in power of 9 Pascal. So we get deformation. The value of deformation is 4.367 multiplied with 10 power of negative 8 meter. So in this video I already covered the learning outcome number 3, learning outcome of mechanics of material.